My students, Assalamu alaikum. I hope you all are fine. Today I am with the second lecture on glycosidic bond titled alpha D glucose and beta D glucose. From this lecture we will try to learn simple chain structure of glucose, structure of D and L glucose, alpha D and beta D glucose, ring structure of alpha D glucose and beta D glucose. So let's try to learn one by one. My students, first of all we will try to learn the simple chain structure of glucose. This is the molecular formula of glucose we know, and let's write the name of this compound, that is glucose. It's a kind of carbohydrate, and this is a member of sugars, so it's a kind of sugar. But what is its structure formula? Let's try to learn. When this compound is treated with hydrogen iodide in presence of red phosphorus is most common allotropes of phosphorus. When glucose is treated with hydrogen iodide in presence of red phosphorus, then N-hexane is formed, which proves that it has 6 carbon atoms. So N-hexane, that means it has 6 carbon atoms, 1, 2, 3, 4, 5 and 6. So 6 carbon atoms. Secondly, when glucose is treated with aqueous bromine, then gluconic acid is formed, which proves that it has 1 aldehyde group. Similar experiment when glucose is treated with Tollens reagent, which we have learnt in Carbonyl compounds chapter, then silver mirror is formed, that is identification of aldehyde group. So it proves that presence of aldehyde group. Similar experiment when glucose is treated with Fehling's solution, then red precipitate of cuprous oxide is formed, that proves the presence of aldehyde group. Again, when glucose is dealt with acetic anhydride in presence of pyridine, glucose pentaacetate is formed, that proves it has 5 hydroxyl groups. Okay, let's write the groups one by one. It has aldehyde group with this carbon aldehyde group and 5 hydroxyl groups. Let's write 5 hydroxyl groups. 1, 2, 3, 4 and 5. The other hands of carbons are satisfied with hydrogen atoms. So from these data, German scientist Bayer proposed this simple chain structure of glucose. Okay, let's move on to the second point. My students, our second point is D and L glucose. From the first learning point, we have learned the simple chain structure of glucose. But at this moment, we will have to learn what is chiral carbon or chiral center. Let's see, in this compound, there are 1, 2, 3 and 4. So in this compound, there are 4 chiral carbons. So let's try to recall what chiral carbon is. According to the definition, the carbon with 4 different groups in its 4 hands. 4 different groups in its 4 hand. This is chiral carbon. Let's see here. This carbon in its 4 hand, one hand hydrogen, another hand another hydrogen, OH, and another hand this portion. So large portion. So this carbon, where the 4 groups are not different, here this is and this is same, so this is not chiral carbon. But here we see this carbon, one hand hydrogen, another hand this portion, one hand this one, and another hand this portion. So this carbon having 4 different groups in its 4 hands. So this is chiral carbon. Chiral carbon is indicated by asterisk. So this is chiral carbon, this is chiral carbon, this is chiral carbon, and this is chiral carbon, because in these carbon atoms, in their 4 hands, there are 4 different groups. According to the formula, how can stereoisomers it can show? Let's see. There is a formula 2 to the power n. N is number of chiral carbons. Here 2 to the power 4. That means 16. So this compound can form 16 stereoisomers. Let's write 2 isomers from the 16 isomers. My dear students, from these 16 isomers, stereoisomers of glucose, I wrote here 2 isomers. Let's look at the structures. Here CH2, CHO, CHOH, 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 CHOH. Same structure. Where is the difference? This is the chiral center, this is chiral center, this is chiral center, another chiral center. This chiral center is termed distant chiral center. So at the distant chiral center, the large group, hydroxyl group, is on the right side. So based on this point, it is just termed D-glucose. But if we see this structure, the distant chiral center contains hydroxyl group on the left side. Based on this point, it is termed L-glucose. So which one is D-glucose? When last chiral center or distant chiral center contains hydroxyl group on the right side, then it is D-glucose, and when last chiral center contains hydroxyl group on the left side, then it is indicated by L-glucose. Now we will try to learn alpha D-glucose and beta D-glucose. Dear students, now we will try to learn alpha D-glucose and beta D-glucose. That means dealing with only D-glucose. This portion CHO, this portion can be written as a structure formula like this: CHO, O and H. When this oxygen group is on the right side, then it is termed alpha D-glucose, and this bond can be rotated freely. Single bond can be rotated freely. So another stereoisomer may be like this. Now we see oxygen group is on the left side. So when this carbonyl oxygen is on the left side, then this glucose is termed as beta D-glucose. Dear students, this is D-glucose. The distant chiral center contains hydroxyl group on the right side. That's why it is termed D-glucose. From these 16 stereoisomers, the structure of D-glucose is proposed by the German chemist Emil Fischer. Let's write the name of the scientist's name. So dear students, now we will try to learn in detail alpha D glucose and beta D glucose. Dear students, now we will try to learn alpha D glucose and beta D glucose. That means dealing with only D glucose. This portion CHO, this portion can be written as a structure formula like this: CHO, O and H. When this oxygen group is on the right side, then it is termed alpha D glucose, and this bond can be rotated freely. Single bond can be rotated freely. So another stereoisomer may be like this. Now we see oxygen group, now we see oxygen is on the left side. So when this carbonyl oxygen is on the left side, then this glucose is termed as beta D glucose. Now we learnt D glucose, L glucose based on hydroxyl group, and alpha D glucose based on carbonyl oxygen. Alpha D glucose and beta D glucose. Alpha D glucose, when carbonyl oxygen is on the right side, then alpha D glucose, and when carbonyl group is on the left side, then it is termed beta D glucose. Dear students, this is the Emil Fischer's D glucose structure. Here we see aldehyde group, but there are some limitations of this structure. It has aldehyde group, but spectroscopic experiment cannot find the presence of aldehyde group. Again, it cannot recover the color of the Schiff's reagent. That's why the cyclic structure of D glucose is proposed. Let's see the cyclic structure of D glucose. My students, now we will try to learn the cyclic structure of D glucose. Now our dealing is only with D glucose, not L glucose. So before going to the cyclic structure of D glucose, one established and very common reaction, we have to see the reaction between a carbonyl compound and alcohol. Let's see the reaction. This is a carbonyl compound. Here this bond becomes polarized, it becomes negatively charged and it becomes positively charged. When here the bond is polarized, then it becomes plus and it becomes minus. So this plus comes here. Now let's write the compound: hydrogen, carbon and another alkyl group, this oxygen with this hydrogen, and this carbon, this plus and this minus. So oxygen and another alkyl group. So from this reaction we see that, from the reaction between carbonyl compound and alcohol, we see that a new bond is formed, that is carbon, oxygen and carbon, carbon, oxygen and carbon, alkyl group carbon. So a new bond is formed. When carbonyl compound reacts with alcohol, then this type of compound is produced. Here similarly we see that here there is a carbonyl group, there is a carbonyl group and alcohol group. So intramolecular reaction happens here, intramolecular reaction happens here, and we will get the cyclic structure of D glucose. Let's write the cyclic structure of D glucose. My students, now I am trying to write the cyclic structure of D glucose. here the reaction between carbonyl group and hydroxyl group happens, and then we will get a new bond, carbon, oxygen and carbon. A new bond is formed. Here OH plus hydrogen, CH2OH, HOH, 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 H, and here a new bond is formed, that is carbon, oxygen and carbon. So this is the cyclic structure of D-glucose, but it is called alpha D-glucose based on this point, that is hydroxyl group is on the right side. That is why it is called alpha D glucose. When it will remain on the left side, then it will be beta D glucose. So this is the cyclic structure of D glucose, that means alpha D glucose and beta D glucose. This structure cannot explain the structure of the polymer cellulose and starch. This is the monomer and polymer is cellulose and starch, but it cannot explain the structure of cellulose and starch. So English scientist Haworth proposed the another structure of glucose. Let's see the Haworth structure of alpha D glucose and beta D glucose. My students, our last point is Haworth structure of D glucose. That means hexagonal ring structure of alpha D glucose. This is alpha D glucose as well, but this amylphous alpha D glucose cannot explain the structure of starch and cellulose accurately. That's why, to dismiss this disadvantage, English chemist Haworth proposed the hexagonal ring structure of alpha D glucose. Let's see the hexagonal ring structure of alpha D glucose. In this structure there are 6 members. Those are 1, 2, 3, 4, 5, and another member is here oxygen, that is sixth member. So in this structure there are 6 members. Let's write the ring structure with 6 members. Here this carbon 1, member 1, 2, 3, 4, 5, and this one is another member, so 6. So this is hexagonal ring structure. Now we will write the groups which are on the right side will be written which are on the left side. Actually the groups which are on the left side will be written above the plane. Now this ring structure is considered a plane, and the groups which are on the left side will be written above the plane. Let's write this carbon number 1. This is on the left side, so it will be written above the plane, and this is below the plane. And second carbon, this hydrogen above the plane, this is below the plane. Carbon number 3, this is above the plane and this hydrogen is below the plane. Carbon number 4, this is above the plane, this is below the plane, and carbon 5 here hydrogen, and it is written above the plane. So this is the hexagonal ring structure of alpha D glucose proposed by English chemist Haworth. Let's write the name of this structure, alpha D glucose. Now we will try to learn the ring structure of beta D glucose. My students, this is Emil Fischer structure of beta D glucose. Here beta refers to hydroxyl group at the carbon number 1, which remains on the left side. That's why it is indicated by beta. And D, we know the hydroxyl group at the distant chiral center. So it is beta D glucose. And we know what is the limitation of this structure, and that's why Haworth structure is determined. Now let's write the Haworth structure of beta D glucose, hexagonal beta D glucose. Let's write. Here there are 6 members, 1, 2, 3, 4, 5, and oxygen another member, so 6 members. Let's write. And like previous one, the groups which are on the left side will be written above the plane. So first carbon atom, this is on the left side, so above the plane, and this hydrogen is below the plane. Carbon 2, this is above the plane, this is below the plane. Carbon 3, this is above the plane, below the plane. Carbon 4, this hydrogen above the plane, this hydroxyl group below the plane. Carbon 5, this hydrogen is written below the plane, and this group is written above the plane. Now we got the hexagonal ring structure of beta D glucose. Dear students, this is the ring structure of beta D glucose. We will see now together hexagonal ring structure of alpha D glucose and beta D glucose. So let's see. My dear students, now we are going to see the hexagonal ring structure of alpha D glucose and beta D glucose together to find the minute difference in the structures. Here we see alpha D glucose, that is hydroxyl group at carbon 1 is below the plane. When it is below the plane, then it is termed alpha D glucose, and other part will remain same. If we see beta D glucose, the carbon 1 where hydroxyl group is above the plane, then it is called beta D glucose. So where is the difference only? Difference only at carbon number 1. Hydroxyl group below the plane, then alpha D glucose, and hydroxyl group above the plane, then beta D glucose. So we got Haworth structure of alpha D glucose and beta D glucose. So that's all about alpha D glucose and beta D glucose. Thank you very much.